Hello everyone and welcome. I'm Ahmet Emre Usta and today I'll be demonstrating my course project for AIN 413 Machine Learning for Healthcare at Hacettepe University, a comprehensive framework for privacy-preserving electronic health records. The digitization of healthcare brings immense benefits but also critical privacy challenges. Electronic health records, or EHRs, contain our most sensitive personal data. As highlighted by researchers, protecting this data from breaches and misuse is paramount, especially in an era of increasing cyber threats and the application of advanced AI like large language models in healthcare. This project aims to tackle these challenges by developing and evaluating an integrated framework that combines multiple privacy-enhancing technologies to enhance EHR security, preserve patient trust, and ensure compliance with standards like HIPAA and GDPR. Our framework integrates 5 key privacy techniques: data anonymization, including K-anonymity, L-diversity, and T-closeness; statistical privacy via differential privacy; cryptographic privacy through a simulation of homomorphic encryption; and robust access control using a role-based access control or RBAC system. The novel contributions include this comprehensive integration, a specialized T-closeness implementation using Earth-Mover's distance for healthcare data, and a pragmatic educational simulation for homomorphic encryption that demonstrates its workflow and prepares for future full integration, addressing common library installation challenges. We validated this framework using a subset of the well-known MIMIC3 clinical dataset, processing 129 patient admissions. This interactive Streamlit demo allows us to explore each of these techniques. Using the sidebar, we can select a specific privacy method or view an integrated analysis. Let's begin with K-anonymity, a foundational anonymization technique. K-anonymity ensures that each record in a dataset is indistinguishable from at least K1 other records with respect to a set of quasi-identifiers, attributes like age or gender that could be used to re-identify individuals. Here, we can set the K value and select our quasi-identifiers. Let's apply it with K equals 3 using age, gender, admission type, and ethnicity. The framework processes the data and we can see the results: the number of records retained, the data retention rate, and processing time. Importantly, it verifies if K-anonymity is satisfied. We can also compare the original data sample with the K-anonymous output, noticing how generalization or suppression might have occurred to meet the K value. Next, L-diversity. L-diversity to address some limitations of K-anonymity, particularly regarding sensitive attribute disclosure. It ensures that within each group of K-anonymous records there are at least L distinct well-represented values for sensitive attributes like primary diagnosis. We'll set L equals 2 and a base K equals 2, focusing on the primary diagnosis. The results show the data retention and processing time. The diversity analysis indicates the minimum diversity achieved within equivalence classes and the compliance rate. If L is too high for the dataset, we might see significant data loss, as was the case in some of our scientific tests with L equals 3 on this specific dataset configuration, where no records were retained. Now for T-closeness, another advancement over L-diversity. Our framework features a novel implementation using Earth-Mover's distance. T-closeness requires that the distribution of a sensitive attribute within any equivalence class is close, within a threshold T, to its overall distribution in the entire dataset. Let's try T equals 0.6 with K equals 2. A higher T is more lenient. The results indicate if T-closeness is satisfied, the maximum observed distance between distributions, and the compliance rate. In our comprehensive back-end test using the specific dataset and QUISA configuration, T-closeness proved very stringent, often leading to high or complete data suppression, as indicated in our report. The demo allows you to experiment with parameters. Sometimes for smaller or sparser datasets, achieving T-closeness without significant data loss is challenging. As we can see here, for these parameters and this dataset, no record satisfied the T-closeness requirement. This highlights its strictness. Moving to differential privacy, it provides strong mathematical guarantees by adding calibrated noise to query results, ensuring individual privacy regardless of auxiliary information. The strength of this privacy is controlled by a parameter epsilon. We can set epsilon, lower values mean stronger privacy but more noise, and select a query type. Let's get summary statistics with epsilon equals 1, or the system applies the Laplace mechanism. We can see the processing time and the privacy budget used. Comparing original and private statistics, for example, the mean of a numerical column shows the effect of the added noise. The error is quantifiable. The budget analysis also shows how epsilon is managed across queries. Next, we explore homomorphic encryption. True HE allows computations directly on encrypted data, which is incredibly powerful for privacy. However, as noted in our project documentation, integrating production HE libraries like PyFHL presented significant environmental challenges. Therefore, this component is an educational simulation. This simulation accurately models the workflow, demonstrates CKKS like performance and noise characteristics, and crucially has an API compatible for future integration of a real HE library. It allows us to understand how HE would function within our privacy pipeline. We can simulate operations like addition or multiplication, for example, adding these two healthcare values. The decrypted result includes a small realistic noise factor typical of schemes like CKKS. The framework also simulates secure aggregation and provides estimated performance characteristics. This simulation helps us appreciate both the potential and the current practical considerations of using HE in EHR systems. The true power of this project lies in its integrated approach. Here we can see how these techniques can be applied in a sequential pipeline, providing multi-layered protection. The pipeline will now process the data through K-anonymity, then, if data permits, L-diversity and T-closeness, followed by differential privacy, with the output being ready for HE simulation and governed by RBAC. The results shows the data retention and privacy utility scores at each stage. We can see how data is transformed and how privacy is enhanced layer by layer. The charts visualize this progression. For this specific run, note how the stringent T-closeness stage impacted overall data retention, leading to few or no records in the final protected dataset. This is a key learning about pipeline design. The analysis also includes RBAC compliance details, showing how access control integrates with these privacy transformations, and an overall framework readiness assessment. This project successfully demonstrates a comprehensive framework integrating 5 privacy techniques. Key findings from our report show that techniques like K-anonymity and differential privacy offer a good balance of privacy and utility. T-closeness in its current configuration for this dataset is highly restrictive. The homomorphic encryption simulation provides a valuable educational tool and a pathway for future cryptographic integration. Limitations include the HE simulation, the dataset-specific nature influencing anonymization outcomes, and the need for further testing against sophisticated attacks. However, the framework's modularity and the insights gained provide a strong foundation for future work, as detailed in our scientific report available on GitHub. In conclusion, this project delivers a production-ready educational framework that advances our understanding of applying and integrating multiple privacy-preserving strategies for electronic health records. It highlights the complexities involved and offers a practical approach to enhancing data security in healthcare. Thank you for watching. For more details, please visit the project repository on GitHub and try out the live Streamlit demo. Your feedback is welcome.